In this lecture, I'll describe Lab 4, which is required for CSCE 611 students earning graduate or honors credit, in which case the lab makes up 15% of your final grade. But it is optional extra credit for all other students, which allow them to earn up to 15% extra credit. Lab 4 builds on Lab 3 and requires that you convert your CPU to a design that can execute up to 2 instructions per cycle. For this, we will group each pair of instructions in your code and fetch them as 64-bit units. For this, you need to increase the width of your instruction memory from 32 to 64 bits, and then in your RISC-V program, you need to remove all even-numbered new lines from your memory ROM file, assuming that the numbering starts at 0. This will place the even-numbered instructions in bits 63 down to 32, and the odd-numbered instructions in bits 31 down to 0. In order to exploit this parallelism you get from 2 instructions per cycle, you'll need to make sure that your program follows 2 rules. Rule number 1, branches and jumps can only appear in even-numbered instructions. And likewise, all branch and jump targets must be even-numbered instructions. Also, any odd-numbered instruction that immediately follows a taken branch or a jump will still be executed even though it appears in your code after the branch or the jump. Rule number 2, any odd-numbered instruction that reads a register written by the previous even-numbered instruction, the immediately previous even-numbered instruction, will be read as the value previous to the previous instruction. So in other words, if you read a register in an odd-numbered instruction, you can expect that register not to reflect any writes to that same register in the previous instruction. The hardware changes are relatively minor. In addition to increasing the instruction memory width to 64 bits, as I mentioned earlier, you should increment your program counter by 2 every cycle, but delete the least significant bit of the PC when connecting it to your instruction memory address. Now you might say, well, this seems kind of redundant, right? You're incrementing by 2, but you're deleting the least significant bit of the address, so it looks like you're just incrementing by 1. Yes, but the reason we do that is because the branch and jump addresses still need to be calculated according to the program counter being word addressed. So the PC will still have a value that is addressed by words and not double words. You will need to add 2 read and 1 write ports to your register file. So this will increase the number of read ports to 4 and the number of write ports to 1. And you have to further make sure that you adjust the bypass logic in the register file to forward a value written on either port, giving priority to port 2. In other words, read data 1 to read data 4 should be able to output write data 1 or write data 2 depending on the circumstances. So this is designed for the case where you have simultaneous register reads and writes in the same cycle due to a data dependency between instructions in the write back and execute stages. So in other words, if you write a register in a pair of instructions and then read from that register in the next pair of instructions, you need to be able to support that in your register file and be able to bypass from either of the 2 write ports to any of the 4 read ports. Finally, you'll need to add an additional ALU and an additional control unit. Once you do this, we ask that you will convert your square root code from Lab 3 into a VLIW form with the objective of speeding up its execution relative to your original CPU by at least 1.3 or 30% faster. To convert your code to VLIW form, you can start out by adding a no-op instruction to every other line of your program, which will place a temporary empty second slot to each instruction. And once you've done that, you will fill in as many of those no-ops as you can according to whenever it's possible to do so without breaking rules. So to demonstrate this, let's do this to a snippet of my permutation code from lecture 9. So I'm showing here the innermost loop from that code, starting from the VLoop target and ending with the branch to VLoop. First, I'll add no-ops to every other line. In this state, the code will run the same way as it did on the single issue CPU. Next, you need to look for opportunities to move an instruction that has a trailing no-op into the position of a trailing no-op of another instruction. And this one move, doing this just once, actually eliminates 2 no-ops and allows 2 instructions to be executed in the same cycle at the target address, the target VLIW packet, instead of 1. Remember that you can't move branch or jump instructions or any instructions that use a value computed by the previous instruction. Also, you must be careful not to violate any register dependencies. In this case, we can combine the first pair of instructions. The 3rd and 4th instructions have a dependency, but we can move the add-I from the bottom of the loop body all the way up under the SLL instruction, since that add-I is just a simple loop counter and no instruction except for the last branch depends on it. So we're free to move that anywhere in the loop body as long as it gets executed on every iteration of the loop. Then we can move the not instruction to underneath the and instruction, despite the fact that the not instruction is in a potentially skipped section of the code. But doing this won't cause any harm. The effect of this move is that it will execute the not instruction even if we would have normally skipped it, but because the not instruction doesn't have any damaging side effects, it doesn't matter. We can move the or instruction, which is another instruction from that potentially skipped section of code, to the slot after the BNAS instruction. So that instruction will be executed regardless of the outcome of the BNAS instruction, but that's okay. Normally, in our original code, it would have only been executed if the BNAS wasn't taken. In this case, it'll be executed whether the BNAS is taken or not. The and SLL instructions can be combined, as well as the or and add instructions. And finally, the store word instruction and add-I instruction can also be combined. And yes, I'm aware that we're not implementing the store word instruction in your lab, but this is just to demonstrate how you would combine these instructions. So we were actually able, in this case, to eliminate all the no-ops in the code except for one at the end. Since we don't know how many times the BNAS instruction will be taken versus not taken, there's no way to know the speed up of this code as compared to our single issue CPU until we run it and count the number of cycles needed for both versions. And obviously, it would depend on the input as well. Since we only expect a few students to submit this lab, we aren't planning to publish a formal lab sheet, but if you have any questions about this, please let us know. You would just submit this using the Lab 3 skeleton, and you just need to make sure that you have all of the requirements in your code. We grade these using a more manual process than we do the normal lab, so we will be sure to look inside your submission and check for all the requirements. And again, if you have any questions, let us know, and good luck.